Katawa. My name is Ayushi, and I'm a fourth year / Master's in Astronomy student. When I was given this opportunity to present a lecture to you guys about chaos theory, I thought it was a good chance to be able to learn more about how exactly chaos is applicable to the orbital dynamics of our solar system. So in this lecture, I'll be first talking about the basics of chaos theory, talking about some theories and concepts, and then we're gonna apply those in different ways to examples from our solar system. Alrighty, so just a little bit of background. So basically, this field of dynamics started in the 1600s with Newton. Newton, we know he did a lot of things, but what's relevant to this discussion is that he solved the two-body problem. I will be talking about this later on, but for now, what you need to know is that the solution of the two-body problem, it basically led to the development of chaos theory, perturbation theory, and chem theory, which are some of the core concepts to be able to understand chaos in the solar system. So what exactly is a dynamical system? It's a system which is evolving in time and is continuously changing, and an example of a dynamical system is a chaotic one. So a chaotic system's motion is evolving in different ways depending on the initial conditions. So that's quite important to remember, that chaotic systems are highly sensitive to their initial conditions. Okay, so that brings us to the question, what exactly is chaos? The definition of chaos is different depending on who you're talking to. I quite liked this definition from the course textbook, Goldstein, which states that chaos is a type of motion which lies between the regular deterministic trajectories arising from solutions of integrable equations and a state of noise or unpredictable stochastic behavior which is characterized by complete randomness. So what that basically means is that chaos isn't exactly, in this context, it's not completely random or unpredictable, nor is it deterministic. It's just a type of motion which lies in the middle of those two extreme ends. Okay, so getting into the nitty-gritty, perturbation theory. So we can describe a dynamical system in terms of its Hamiltonian, which is integratable. So integratable means that a solution can be found. Non-integratable means we can't find a solution. So when our integratable Hamiltonian becomes perturbed, i.e. there's a small disturbance, it becomes non-integratable. So let's assume there's a Hamiltonian H, which involves a dominant interaction from an integratable Hamiltonian, in addition to a small perturbation term, delta H. I'm just going to emphasize the use of the word small. We're talking about small perturbations and not large ones. So we can describe that by this equation here, where the Hamiltonian is given by the integratable Hamiltonian plus the small perturbation term. So then we can use a generating function of this general form to be able to transform the dominant Hamiltonian with the phase-space coordinates P and Q to the new coordinates capital P and Q of the transformed Hamiltonian, which we're going to call K naught of capital Q and P. So we ensure that the new variables are constant in time by having the transformed Hamiltonian, K naught, equal to 0. And then we get this equation where the transformed Hamiltonian is equal to the integratable Hamiltonian plus the partial derivative of the generating function with respect to time. And if we equate this to 0, and using Hamilton's equations, then we get new coordinates in momenta, capital Q naught and P, which are constants of the motion. And so using the same transformation as this first equation over here, we get a transformed Hamiltonian delta K naught, from which, again using Hamilton's equations, we get first order perturbations described by these two equations over here, which I'm sure looks familiar to a lot of you, having done a whole assignment on that. Okay, so the point that I'm trying to make here is that this method iteratively provides good approximations to the solution if we have a small perturbation term, delta H, present. Perturbation theory is extremely useful to be able to find an approximate solution for a problem which is unsolvable, which is non-integratable. And the more higher order perturbation terms you have, the better approximation of the solution that you get. Yeah, so Newton basically spawned the development of perturbation theory. And when he tried to, so once he solved the two-body problem and people tried to solve the three-body problem, they found that it's impossible to solve without using perturbation theory. Okay, moving on now to the Kolmogorov-Arnold-Moser theorem. So we just obtained a solution for a perturbed Hamiltonian system. Naturally, some questions follow. Number one, is the perturbed solution stable? And number two, will the perturbed orbits remain close to the unperturbed orbits over large periods of time? So this boils down to conditions for regularity, which is described by the Kemp theorem, which states that if the boundary motion of the integratable Hamiltonian H0 is perturbed by a small perturbation term, delta H, then the total Hamiltonian, here, becomes non-integratable. Also, the motion of the system gets confined to an n torus, except for this little exception here, which I'll come back to later. So the motion of the system gets confined to an n torus, which is, we'll think of it as a ring or a donut, if the following two conditions are satisfied, which is that the perturbation term, delta H, is small, and that the frequencies of the integratable Hamiltonian, H0, are incommensurate. So incommensurate means that if you take a ratio of the frequencies, that comes out to be an irrational number. If it comes out to be a rational number, then it's commensurate. Where are we? So Kemp theory implies that the perturbed orbits are stable. They're slightly different in shape compared to the original orbit, but they are localized in the same region as the original orbit. Now, going back to the negligible set of initial conditions, which results in a meandering trajectory on the energy surface, what that means is that there is a possibility of initial conditions for which Kemp theory doesn't hold, which is when chaos can occur. So, as I have just emphasized multiple times, Kemp theory works for small perturbations, but what about for the larger perturbation terms? As an analogy here, we can think about the double pendulum. So, at small angles, the double pendulum behaves approximately like a single pendulum. However, at large angles, or perturbations in a way, the motion, motion of the double pendulum becomes chaotic. So what I'm trying to say here is that if the perturbations are large enough, the system's behavior can become chaotic. Okay, but how do we quantify the chaoticness of the system? One way to do that is using the Lyapunov exponent given by the coefficient lambda. So if we wanted to find the separation, okay, so Lyapunov exponent is my co-presenter Ben's topic, so he's going to go into more detail about this, but for now, just mentioning the relevant bits. So if we wanted to find the separation of orbits for a system in the chaotic region, we can use this equation here, where the separation is given by the initial separation times the exponent of the Lyapunov exponent times time. What's important to note here is that if the Lyapunov exponent lambda is greater than 0, then the system's motion becomes chaotic. Similarly, we can talk about the Lyapunov time scale, which is the time scale on which a dynamical system becomes chaotic. And I will be talking more about these concepts when we get to the applications part of the lecture. Okay, I'm just going to briefly talk about resonances. So in the solar system, there's quite a lot going on in the solar system, including subtle gravitational effects, which determine the dynamics and interactions happening in the solar system. One important effect is that of resonance. So resonance arises when there's a simple numerical relationship between frequencies or periods, i.e., so that relates to the ratio being commensurate, which again I'll be discussing in the examples. So resonance can arise because of the rotational and orbital periods of a single body, that's called spin-orbit coupling, or even because of the orbital periods of two or more bodies, which is called orbit-orbit coupling. So as an example, the Moon-Earth system has the Moon in a 1:1 spin-orbit resonance with the Earth. which by the way is commensurate. Okay, so resonances in the solar system exist for many different bodies, and they create what's known as chaotic zones, or gaps between orbits. And the asteroid belt, which is one of my examples, has actually been shaped because of perturbations and resonances, which are mostly from Jupiter. So what happens is that these resonances in the asteroid belt, they give rise to what's called as chaotic zones, which is where the bodies inside the chaotic zone are affected by the chaos or unpredictability in this zone. Okay. The n-body problem. I'm going to talk about this very briefly. There's also a little derivation in the appendix. You can look over that in your own time, or if there's time I could go over it. We know that Newton solved the two-body problem, and that extends into the three-body problem and then the n-body problem to make it generic. What we find is that for n greater than or equal to 3, the n-body problem becomes difficult to solve analytically. So we can use perturbation theory and QAM theory together to be able to solve approximately the n-body problem. And I'm just going to talk about something called the planetary problem, which is the case of the n-body problem, where one of the masses is much larger than the other masses in the system. So an example of the planetary problem is the Sun, Jupiter, Saturn system, where the Sun is 100 times more massive than Jupiter or Saturn. So we can solve this planetary problem using perturbation theory to give us a good approximation. But this method only works well if there are no orbital resonances in the system. But we do know that resonances exist in the solar system, and we can't just ignore them. So that leads us into questioning the stability of the system with these resonance and perturbation terms present. This is where QAM theorem comes into play. QAM theory tells us that if we apply certain constraints to in this case, the planetary problem, then we get a set of quasi-periodic orbits, which means that there are chaotic planetary orbits, but they're bounded by quasi-periodic orbits. And my co-presenter Ben will be talking more in detail about this notion of quasi-periodicity. But yeah, I just wanted to mention the n-body problem briefly before we move on to applications. So, applications. Okay, so like I said, there's quite a lot going on in the solar system, and we can study the chaos in the solar system in many different ways. There are researchers who dedicate their entire lives to studying the dynamics in the solar system, and they do a lot of studies about these, and so I'll be talking about some studies and some examples from the solar system. Okay, so the first example, we're going to talk about the system's sensitive dependence on initial conditions in the solar system. So this is our system. Let's ignore the trajectories for now. That's the Sun. That is Jupiter in an idealized circular orbit. And here's our test particle. So we can define the particle's motion in terms of its position and velocity vectors in four-dimensional phase space, and as time goes on, the particle follows a trajectory in phase space, as well as its own configuration in space. So now we have two cases to consider. Number one, where the particle is only affected by the gravity of the Sun, and number two, where it's also being perturbed by Jupiter, the planet. So in the first case, where it's only being affected by the gravity of the Sun, we can completely predict the motion of the particle at all times t, because that is a two-body problem, so it can be solved exactly. And in that case, the particle's motion, we say, is deterministic. But in the second case, because of the extra perturbations from the planet, that induces chaos in the trajectory of the particle, which means that the motion of the particle becomes indeterministic. Or, in other words, the Hamiltonian, in that case, is non-integratable. We can't solve this problem exactly. Moving on to the second part of this example. So, same system, Sun, Jupiter in the idealized circular orbit and massless particle. Now we define a set of initial conditions. So this is a fixed set of initial conditions. So we have semi-major axis equal to 0.8, eccentricity equal to 0.4, and longitude of the center omega bar equals 295 degrees. So these are fixed. And now we're going to consider two scenarios where we change one initial condition slightly. So we're going to change the initial condition of something called the initial mean longitude lambda naught. This is not to be confused with the Lyapunov exponent lambda, it's just the notation which the textbook is used. So this is degrees. So that's one of the initial conditions in the first scenario, and the second scenario, the initial condition is 293.3 degrees. This is only a difference of 0.3 degrees. Would you say this is small? Yeah, it is small. It's very tiny. It's a very, very tiny perturbation. But what we get is that despite having these three fixed initial conditions, but just changing one of the initial conditions, it still produces very different trajectories for the test particle, despite this tiny little perturbation. So we can evaluate the KAM theorem in this case. So we have small perturbation, yes. Let's say we have incommensurate frequencies, okay. So KAM theorem holds, but we just noticed that the dynamic system is highly sensitive to the initial condition, the slight change in initial condition. And that produces the chaotic trajectory of the test particle. So from the first part of the example we talked about, we saw that perturbations from the planet also makes the particle's equation of motion non-integrable, i.e. chaotic. Okay. Second example, Pluto. So I'll be talking about a study which investigated the long-term behavior of Pluto. So in Sussman and Wisdom, 1998, they did a numerical integration simulation study of the motion of Pluto. And they conducted their study in the context of deterministic chaotic behavior. They defined quasi-periodic trajectories as being linearly divergent over time, and chaotic trajectories being exponentially divergent over time. So in their integration, they modeled two quantities over an 845 million year period. So the first quantity is the inclination I of Pluto, and the second quantity is h equals e sine omega bar, where e is the eccentricity and omega bar is the longitude of perihelion. They found that the trajectories of both of these quantities, which they modeled, they diverge exponentially. So what does that indicate? It indicates that it's following a chaotic trajectory. Just to back up their finding, they also did calculate the Lyapunov exponent for their simulations. And yes, sorry, this is a typo. So the largest Lyapunov exponent that they found was 1 times 10 to the minus 7.3 per year. That's positive. And after doing a couple more calculations in their paper, they found that the trajectory of Pluto's orbit starts exponentially diverging, i.e. chaotic, becoming chaotic, after 20 million years, which, considering their simulation period, 845 million years, is very, very short. So in the paper, they concluded that Pluto's orbit is deterministically chaotic. So just from the concepts that we talked about earlier, they found that the motion of Pluto is chaotic over long timescales, and they calculated the Lyapunov exponents, which is positive, which tells us that Pluto's trajectory is chaotic. Let's evaluate the KAM theorem. Does it hold in this case? It doesn't. It doesn't hold in this case because Pluto is actually being perturbed by other small bodies, including Neptune and other small bodies. But also from this other study, we know that Pluto is in a 3:2 mean motion resonance orbit with Neptune, which is commensurate because 3 over 2 is 1.5, that's commensurate. So KAM theorem doesn't hold in this case. Okay, last example, the asteroid belt, which I had mentioned before when talking about resonances. So the asteroid belt is located between the orbits of Mars and Jupiter, and it contains many asteroids, which are called minor bodies. So multiple studies have been able to study chaos in this region. In this paper, Milani and Romilli, 1996, they studied the Lyapunov exponent of asteroids in the asteroid belt. And they found that the maximum Lyapunov exponent of these asteroids is actually very large. They're all positive, by the way, with a corresponding Lyapunov timescale on the order of 100,000 years, which is very short. They concluded that the asteroids are cases of what's called stable chaos, which means that it's related to the high order resonances and perturbations from Jupiter, which is what is driving the chaos being found in the orbits of these asteroids. And in the second paper, they investigated the effects of perturbations from Jupiter on the asteroids, but they also took into account the perturbations of Jupiter by Saturn. And what they found was that Saturn actually introduces additional frequencies into Jupiter's orbit, which in turn produces chaos in the chaotic zones, which are associated with the mean motion resonances between the asteroids and Jupiter. And basically, the study demonstrated that the consideration of perturbations in and that's the title again, should be N-body problem, also taking into account resonances creates chaos. And once again, evaluating the CAM theorem, it doesn't hold in this case because the perturbations, when coupled with the resonance, creates larger perturbation effect. In addition to which, the resonances are commensurate from numerous studies done in that region. Okay, so to conclude, we talked about chaos theory and some concepts related to chaos theory, and then we applied this to the solar system. The point that I'm trying to make, or I tried to make during this presentation, is a study of ways that chaos occurs in the solar system. And we saw that happens in different ways. So in the first test particle Jupiter example, we saw that changing the initial conditions slightly led to chaos. We saw that large perturbation effects leads to chaos because CAM doesn't hold in that case, CAM theorem. If the Lyapunov exponent is found to be positive, greater than 0, that also is an indication of chaos. And resonance creates chaos in chaotic zones. So the idea is that we can use these concepts and theories, plus the N-body problem, to be able to simplify our understanding of the many dynamics going on in our solar system related to chaos. There's a lot of chaos in the solar system. So yeah, if you're interested in learning more about chaos or dynamic systems, you can do this course, Math 6.3, which talks more about that. Yeah, so thank you. I hope you guys like that.